The Sun is just one of 100,000 million stars in our galaxy. It makes up 99% of the solar system's mass, and its gravitation holds all the planets in their orbits. The Sun is a giant nuclear furnace that bathes the planets in warmth and light. Life on Earth depends on this energy. The Sun's immense gravity squeezes hydrogen atoms together to form helium, liberating vast amounts of energy. The high temperatures rip electrons from their atoms, resulting in highly charged plasma, the fourth state of matter. Its surface is a tangle of surging magnetic fields, regularly ejecting gigantic clouds of charged particles. If they collide with Earth, the effects can be drastic. Power supplies can be overwhelmed. Spacecraft have been knocked out of orbit, and communications systems relying on satellite relays have gone black. There are fundamental questions about the Sun's behavior that modern science is making great efforts to answer. Scientific studies of the Sun started in the early 17th century, when Galileo turned his telescope to the heavens. Various observers began documenting sunspots' movement across the solar disk. In the 19th century, after gathering data for 25 years, Heinrich Schwabe noted a regular pattern of sunspot activity that followed an 11-year solar cycle. During this cycle, the Sun shows very little sunspot activity at solar minimum, on the left, when solar storms are infrequent. At solar max, on the right, sunspots proliferate and giant solar flares are common. When astronomers learned to predict eclipses, a new type of solar investigation opened. With the Sun obscured by the Moon, it became clear that it was surrounded by a vast and intricately patterned aura that became known as the corona. Using a spectrograph, British astronomer Norman Lockyer analysed the inner corona. He saw a previously unknown element. It became known as helium, from the Greek helios, the sun. As electrical technologies like telegraphy became common, new phenomena were noticed. In 1859, English astronomers Richard Carrington and Richard Hodgson recorded a solar flare. While observing a group of solar spots on the 1st of September, I was suddenly surprised at the appearance of a very brilliant star of light, much brighter than the Sun's surface. Richard Hodgson. At the same time, magnetometers at the Kew Observatory recorded strong magnetic activity. That night, auroras stretching from the poles to the tropics were seen, and telegraph operators around the world reported sparking wires and electric shocks. While Carrington and Hodgson accurately recorded their observations, they were reluctant to link auroras to solar activity. Modern science accepts that what is now called the Carrington event was the greatest coronal mass ejection to hit the Earth in modern history. Early in the 20th century, Norwegian physicist Christian Birkeland observed that an electron beam directed toward a spherical magnet produced rings of light around the poles. He proposed that rays of electric corpuscles from the Sun could impinge upon the Earth's poles in the same manner, resulting in auroras but his theory was disregarded. Space-based science began in 1946, when the United States, using captured V-2 rockets, made ultraviolet observations of the Sun. Most UV cannot be observed from the ground because it is blocked by atmospheric ozone and oxygen. The work continued over a series of flights, eventually leading to spectral evidence of highly charged iron in the solar corona. Only extreme temperatures, millions of degrees Kelvin, could account for the results. This means the Sun's varying corona is around 200 times hotter than its surface. How could this be? In 1963, a research satellite, Transit 5E1, was launched in tandem with an early navigation satellite. Transit 5E1 went into a polar orbit to study charged particles, magnetic fields, and solar spectra. Detailed analysis of the data returned by Transit 5E1 showed a clear link between charged particles above the poles, solar activity, and auroras. Proof that Birkeland's theory was correct. Today, we understand that auroras are caused by protons, electrons, and alpha particles with traces of heavier ions ejected from the Sun. Most are deflected by the Earth's magnetic field, but some spiral into the atmosphere along the Earth's magnetic field lines. The particles interact with oxygen and nitrogen in the upper atmosphere. At times of heavy solar activity, auroras can stretch further north or south from the poles. While nuclear physics had revealed how the Sun, as a giant fusion reactor, converted matter into energy, there were very puzzling questions about its behavior. In the 1950s, American physicist Eugene Parker proposed a theory suggesting that a constant stream of ions flowed from the Sun. It was called the solar wind. And again, the idea was largely ignored. But this was the space age, and soon spacecraft from the Soviet Union, as well as the US Mariner 2 mission, began detecting the solar wind. The theory became fact, and Eugene Parker continued to play an important role in heliophysics well into the 21st century. As space technology grew more complex, with increasing reliance on satellite communications, research missions began observing the Sun more closely, and a new term, space weather, entered the lexicon. Space weather can result in increased atmospheric drag on low-orbiting satellites. It can push geosynchronous satellites out of position, and clouds of plasma can even kill satellites. In 1973, at the end of NASA's Apollo program, a highly modified Saturn V was prepared for a very different mission. Skylab was to be the United States' only independently operated space station. The rocket's upper stage would not be used for propulsion. It had been equipped as an orbital laboratory.
11, 10, 9, 8. We have ignition sequence has started. 6, 5, 4, 3. And we have a liftoff. The Skylab lifting off the pad now, moving up. Skylab has cleared the tower.
One of its major tasks was to serve as a solar observatory. The images it captured and the scientific return represented a breakthrough in solar physics. Skylab pushed 1970s technology to the limits. A cluster of 6 telescopes recorded solar behavior in various ultraviolet and X-ray parts of the spectrum not visible through the Earth's atmosphere. The telescope cluster originally intended to be mounted on an Apollo spacecraft, could not be reached from within the laboratory. Yet the images from all but one of these instruments had to be recorded on film. This required the crew to leave the Skylab periodically to exchange the film canisters. Earthbound astronomers were initially skeptical of the solar observations that Skylab was asked to do. But as the exposed film returned to the ground, they realized that both the quantity and quality of the data would keep analysts busy for years. Skylab delivered the first images of solar flares, and holes in the corona and X-ray bright points were also discovered. Film was still the primary recording medium because it offered far greater resolution than the slow scan television systems available at the time. But film had to be returned to Earth to be processed and viewed. While this was feasible with orbiting missions like Skylab, engineers realized that they would have to devise a high-definition system for deep space missions that could not return to Earth. Since the 1600s, astronomers have made estimates of the sun's rotation by tracking sunspots. But the sun is not solid, and at high latitudes, the spin rate is different. Viewed from the Earth, our star's equator spins once every 25.5 days and once every 33.5 days at 75 degrees latitude. All the planets in our solar system orbit in the same direction as the sun's rotation and roughly in the same plane, the ecliptic, as the sun's equator. This means we cannot see the sun's polar regions from the Earth. In 1990, a joint mission between NASA and the European Space Agency was launched from the Space Shuttle Discovery. Called Ulysses, it first traveled to Jupiter to use the giant planet's gravity to loop beneath the ecliptic and back toward the Sun. This would give Ulysses the opportunity to gather solar data from every possible angle, including the poles. Over a 17-year period, more than one complete solar cycle, Ulysses orbited the Sun 3 times and discovered that its magnetic field flips every cycle, and it observed the solar wind from the poles traveled faster than that from the equatorial regions.
3, 2, 1, ignition. And liftoff of SOHO and the Atlas.
In 1995, another ESA-NASA joint mission launched. The Solar and Heliophysics Observatory was put into orbit around the first Earth-Sun Lagrangian point. Among its 12 instruments were a coronagraph and a unit called GOLF, from global oscillations at low frequencies. The coronagraph is a telescope with an inbuilt disk that masks the sun to enable detailed observations of the corona. Barely 2 years into its operations, 2 of SOHO's 3 gyroscopes failed and the craft began tumbling. It took months to reacquire a signal and then slowly regain control. SOHO's operational software was rewritten to allow it to function without gyros. Since then, SOHO has functioned flawlessly, and its contributions have been significant. The probe's GOLF instrument has measured vibrations from the sun similar to quakes on Earth, allowing scientists to picture the solar core. It spins roughly 4 times faster than the rest of the sun. The probe made breakthroughs in our ability to see writhing magnetic features like giant looping flares and solar tornadoes. For the first time, it was possible to see clearly coronal mass ejections that can bombard the Earth. Early detection allows vulnerable technologies time to prepare. The Sun is a vast tangle of magnetic field lines that affects the whole solar system. We are fortunate that our planet has its own magnetic field. Convection within the Earth's iron-rich core gives our world a magnetic shield that protects us from the worst extremes of solar storms. Solar field lines can connect with the Earth's field lines, conducting vast amounts of charged particles into the geomagnetic system. When the connection breaks, the particles blast into the upper atmosphere, and we see auroras like these viewed from the International Space Station. Because of our reliance upon technologies that are vulnerable to these high-energy particles, NASA built a suite of satellites to learn about the complex magnetic interactions taking place around the Earth, particularly during heavy solar activity.
0. And liftoff of the Atlas V with MMS using magnetic reconnection.
The Magnetospheric Multiscale Mission, or MMS, was launched in 2015. The 4 spacecraft gradually separated. Then each deployed a series of radial and axial booms, enabling them to measure hot plasma, energetic particles, and both magnetic and electric fields. The probes dispersed into a tetrahedral formation using GPS signals from the ground to lock into position. This allowed them to accurately map, in 3 dimensions, the electromagnetic activity at the boundary of the Earth's magnetic field. The MMS probes were the first to directly register reconnection events. They are helping us understand the transfer of energy at reconnection and the acceleration of particles. The MMS probes are expected to continue in service until 2040. A similar mission is soon to go to Mars. Our neighboring planet has very little atmosphere and a very weak magnetic field. Water once flowed on its surface. NASA's ESCAPADE mission will find out what role the solar wind could have had in stripping away the Martian atmosphere. Sunspots are more frequent during periods in the solar cycle of great activity. These are the times when huge ejections of coronal material can sweep toward the Earth, with major consequences for communications, navigation, and electrical power grids. While there are techniques to predict developments on the far side of the Sun, they are inaccurate. A pair of solar satellites observing the Sun from different angles could monitor solar activity everywhere. The 2 stereo probes were launched in 2006. They separated and initially headed toward the Moon. Arriving at different times, they used the lunar gravitation to further separate along a sun-centered orbit. Their positions continued to diverge, ultimately allowing a combined view of the complete Sun. Each spacecraft is fitted with cameras, particle experiments, and radio detectors. Their microprocessors are radiation hardened to resist extremes of the solar environment. 2 differing aspects of solar storms were of interest to the stereo team. Coronal mass ejections, here seen from Stereo A's coronagraph, happen when magnetic field lines break, blasting billions of tons of solar plasma from the corona out into space. If it's on a collision course with Earth, it will take between 1 and 3 days to arrive. Solar flares are bright eruptions from the Sun's surface. Brilliant light, including X-rays, will take just 8 minutes to reach the Earth. Data from the stereo satellites improved the accuracy of space weather alerts. In 2012, Stereo A passed through a coronal mass ejection of similar strength to the Carrington event. It survived unscathed and relayed valuable information. In October 2012, NASA lost contact with Stereo B. Subsequent analysis discovered the craft was in a rapid spin. Numerous attempts were made to re-establish control, but after 3 years, recovery operations were abandoned. Stereo A continues in operation. Its off-axis view complements other solar observing satellites. In the year 2000, the still incomplete International Space Station received its first permanent crew. While they orbit well below the Van Allen belts, without the protection of a deep atmosphere, the crew members will still experience higher doses of radiation than people on the ground. Solar storms can further increase the risk to astronauts, so solid information on the sun's behavior became even more important. The following year, NASA established the Living with a Star program. This new program coordinated international solar research with an emphasis on the sun's effect upon the Earth, its people, and its modern technology. Just as meteorologists observe weather patterns around the clock, a new space weather service would continually monitor the sun. Soon, at NASA Goddard in the clean room in Building 29, the first in a new generation of solar monitoring satellites was taking shape as the foundation stone of the Living with a Star program. The new satellite was to be known as the Solar Dynamics Observatory. It was designed so solar physicists could understand solar processes with a view to predicting the behavior of the sun. It had to monitor the complete disk of the sun continuously, and it had to capture high-definition pictures in 10 different wavelengths. The amount of data SDO would generate was huge. No flight-tested recorder could handle the load, so the satellite would have to remain in constant contact with a ground station. A dedicated receiving facility with 2 18-meter antennas was built at White Sands, New Mexico.
4, go for main engine start. 3, 2, 1, 0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory, learning why our star is changing our lives.
It was launched in February 2010. SDO is in a circular geosynchronous orbit inclined at 28 degrees, about the longitude of the New Mexico receiver. It can almost always see the sun while remaining in contact with the ground. Each day above the White Sands facility, it appears to move in a figure of 8. The satellite's atmospheric imaging assembly consists of 4 adjacent telescopes capable of viewing the sun in 10 different regions of the electromagnetic spectrum. In visible light, we can see the surface, the photosphere, at around 5,800 degrees Kelvin. Here we can observe sunspots. Moving up through the inner layers of the corona, the temperatures increase drastically, and the light emitted climbs higher into the ultraviolet, with different features being revealed. By convention, different colors are used to represent the different parts of the extreme ultraviolet spectrum. The 304 angstrom wavelength highlights the transition region from the photosphere to the chromosphere. It is particularly good for observing flares and prominences. The same event viewed at different wavelengths reveals different features. Ordinary lenses are opaque to these high-energy wavelengths, so designers employed curved mirrors to focus extreme ultraviolet light onto the camera's sensors. Not only was the SDO designed to capture high-definition images across the high-energy spectrum, it had to do so at a rapid cadence and over extremely long periods of time. The ground station must receive a downlink rate of 130 megabits per second for months. The data is relayed to several science operations centers, from where it is made freely available to services and researchers around the world. The data flow from the SDO and its rapid dissemination revolutionized solar research and space weather alerts. The US's National Oceanic and Atmospheric Administration operates the Space Weather Prediction Center. Its daily bulletins are important for power infrastructure, communications, and GPS services. If the International Space Station is threatened by a coronal mass ejection, the occupants will shelter in the Russian Zvezda module, the most heavily shielded part of the space station, and non-essential electronic equipment will be switched off. If the approaching radiation appears severe, the crew can rapidly return to Earth in the attached Soyuz or Dragon capsules. So far, this has not happened. Researchers are looking for patterns of solar behavior that might lead to the development of predictive modeling. Almost continuous observation allows statistical analysis of solar events. There is a link between the dimming of the corona and coronal mass ejections, and solar flares are often followed by a secondary late-phase flare. The information is building an important research archive. Yet, heliophysicists digging into sunspot records that have been collected over centuries understand that our star's behavior varies greatly over longer periods. While we speak of a solar cycle of 11 years, it has sometimes been as short as 8 years or as long as 13 years. Researchers think this variation fits into an even longer 80 to 90-year pattern. There appears to be a strong correlation between a sparsity of sunspots, solar dimming, and long-term temperatures on Earth. In 1976, a paper written by astronomer John A. Eddy built upon work from 19th century researchers Gustav Spörer and Edward Maunder. They had identified a period of remarkably little sunspot activity that coincided with a prolonged cold period known as the Little Ice Age, where the Thames in London would regularly freeze over. Tree ring analysis backed this up and suggested a similar period had bridged the 13th and 14th centuries. Realizing this led to new questions about the influence that the sun has on planet Earth's climate. In 1958, the United States' first satellite, Explorer 1, was launched. It was equipped with a modified Geiger counter. Researchers had hoped to detect cosmic rays, high-energy particles from deep space. The instrument registered radiation levels 1,000 times greater than expected. James Van Allen, who had designed the experiment, realized that 2 layers of high-energy particles encircled the Earth, and in 1958 they were named the Van Allen radiation belts. They are areas of highly charged particles from the Sun, trapped by the Earth's magnetic field. In 2012, the Van Allen probes were launched, also as part of NASA's Living with a Star program.
Lift off the Atlas V rocket and twin spacecraft on a mission to unlock the mysteries of Earth's Van Allen belts.
Clearly, what happened at the Sun was only part of the Sun-Earth interaction. The Van Allen belts vary in size and intensity according to solar activity, but this process is not well understood. Most satellites switch to safe mode when radiation levels become critical, shutting down, waiting to be restarted by a signal from the ground. But these are just the conditions that the Van Allen probes were designed to monitor. Their circuitry was radiation hardened and protected by thick metallic shielding. Their highly elliptical orbit had them passing through every level of the inner and outer radiation belts. Although great care had been taken to ensure they could function in this hostile environment, they were only expected to last for 2 years. Launched near the peak of a solar cycle, the two probes promptly returned data revealing the extent of the outer and inner belts, but within days a wave of solar particles swept past the Earth and a new middle ring emerged. Scientists were scratching their heads about the extra radiation belt when another, even larger coronal mass ejection hit, wiping away the outer and middle belts. A week later, yet another cloud of particles hit, restoring the original inner and outer rings. It was thought that the high-energy electrons that had suddenly disappeared had entered the atmosphere. A series of high-altitude balloon flights, launched from both the southern and northern polar regions, was made to detect high-speed electrons entering the upper atmosphere. They were timed with the overflight of the Van Allen probes. The missions detected a rain of energetic electrons entering the upper atmosphere as electrons disappeared from the radiation belts. The Van Allen probes went on to map variations in the electrical complexities of the near-Earth regions for 7 years, far beyond the satellite's expected lifespan. Key questions remain unanswered. How is the surface temperature of the Sun around 6,000 degrees Kelvin, when the corona, the Sun's atmosphere, is between 1 and 2 million degrees Kelvin? And the outflow of solar plasma, we call the solar wind, is accelerated to incredible speed. How? Since the discovery of the solar wind, people like Eugene Parker had called for a probe to be sent into the solar corona. But only recently has the technology caught up to the scientific ambition. Late in 2010, engineers at the Johns Hopkins Applied Physics Lab began work on what NASA refers to as the most autonomous probe ever built. The Solar Probe Plus would have to look after itself for large portions of its mission while it was near the Sun and out of contact with the Earth. The craft was designed to shelter from the intense radiant heat behind a carbon-carbon heat shield, and water would flow through the stubby tips of its solar panels to provide cooling. A year before it was due to launch, Eugene Parker, who predicted the existence of the solar wind, received a phone call.
They've been working on this spacecraft for several years, and one day the phone rang, and a guy that I know said, "We're talking about putting your name on the Solar Probe Plus," it was called. And did I object? And I sort of said, "No, I feel rather flattered." So he said, "Okay, that's what we'll do."
The Parker Solar Probe is the first NASA spacecraft to be named after a living person. The trajectory presented a problem. Anything launched toward the Sun must travel at very high speed to avoid being overwhelmed by the Sun's powerful gravitation. And because the Parker probe had to pass so close, speed records would be broken. The Delta IV Heavy, fitted with a solid-fueled upper stage, was the most powerful rocket available at the time of launch. It was designed for lifting giant communications and intelligence satellites to geosynchronous orbits. The The Parker probe is of modest proportions, and there was plenty of empty space after it had been encased within the Delta IV's launch shroud. The giant rocket was needed for speed. August the 12th, 2018.
7, 6.
The 90-year-old Eugene Parker was there to witness the launch of the Parker Solar Probe.
0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
Fixed to the spacecraft was a plaque with a quote from Parker, "Let's see what we can find out." It was a fitting tribute to a significant figure in science. The PSP left Earth at around 57,000 kilometers per hour. Only the New Horizons probe, bound for Pluto, had a greater departure speed. But New Horizons, traveling away from the Sun, was constantly slowing under the influence of solar gravity. Traveling toward the Sun, the PSP was accelerating. After 8 days, it had already picked up 10,000 kilometers per hour.
Parker Solar Probe is the hardest trajectory that I've ever worked on. The folks at Applied Physics Lab have come up with a very unique trajectory where the spacecraft is going to use the mass of Venus to slow themselves down. And not only are they doing that one time, they're actually going to do that 7 times in a row over a space of 6 years in order to get the spacecraft perihelion, because we're orbiting the Sun, down below 10 solar radii. And therefore, when we pass very close to the Sun, which is the most massive object in our solar system, we are going approximately 430,000 miles per hour relative to the Sun.
It took only 53 days to make its first pass of Venus. Most Venus explorers had taken in excess of 100 days. A spacecraft operating in a weightless environment can be perturbed by the gentlest of forces. Even sunlight can nudge a probe off course. Accurate radio ranging techniques will reveal even the slightest divergence from the desired path. However, the PSP spends much of its time close to the Sun, an unfamiliar cosmic environment. Charged particles will distort positional information, and the probe will be out of contact as the Sun-Earth probe angle narrows. New ways of operating a satellite within this environment are still evolving. The Parker Solar Probe began its first pass of the Sun in November 2018, reaching a close point, perihelion, of 24 million kilometers and a top speed relative to the Sun in excess of 340,000 kilometers per hour. Researchers on the ground had to wait several weeks for confirmation that the spacecraft was functioning correctly and that it had recorded data. It was several more weeks before that data could be downloaded. The probe had passed through several magnetic switchbacks, sudden, brief reversals in the magnetic field lines. These could be the means by which the corona is heated to its extreme levels. To actively align its heat shield toward the Sun, the Parker Solar Probe uses a combination of rotating momentum wheels and thrusters. Engineers were delighted to learn that the craft was so well balanced it was using less fuel than expected for its alignment. Thruster fuel is the limiting factor in most missions. The following year, the Parker Solar Probe made 2 more passes, each one closer to the solar surface and with an increasingly higher top speed. In 2021, during its 8th perihelion, the PSP passed slightly more than 10 million kilometers above the surface at a speed in excess of 530,000 kilometers per hour, continuing to break its own records. NASA has frequently used the expression touched the sun, referring to this and subsequent close passes. This may be poetic, but a more accurate description is that the probe passed inside the Alphen surface, the region of the corona that is still gravitationally and magnetically connected to the sun. It found a lumpy, uneven boundary, and at the closer distance, the magnetic switchbacks were now experienced as strong jets of high-energy particles. Researchers concluded that they must be driven by magnetic reconnection. At this distance, they had a clear direction that could be followed to their source: convection cell structures seen on the face of the photosphere. Tangled magnetic field lines push out along the edges of these cells, propelling charged particles outward. This was a breakthrough in understanding the solar wind. It also captured pictures of solar streamers, previously only visible from Earth during solar eclipses. The only pictures the Parker Solar Probe can deliver are from a camera with a sideways view. It was simply not possible to protect a forward-looking camera from the extreme temperatures. However, a European spacecraft, designed to work with the PSP, now provides images. The closest, most detailed pictures ever made of the sun. The European Space Agency's solar orbiter had been in development since 2011. NASA was a junior partner in the project, supplying one of the spacecraft's instruments and providing launch services. However, it had been delayed while the spacecraft was extensively tested and retested.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And liftoff.
In February 2020, Solar Orbiter successfully began its mission.
To give us new images and a better understanding of our life-giving star.
During the development of the Solar Orbiter, there had been extensive collaboration between NASA and the European Space Agency to ensure that the Parker Probe and the Solar Orbiter would complement each other's investigations. The Solar Orbiter has 10 separate scientific packages: in situ instruments for registering the particles and fields that impinge upon it, and remote sensing instruments primarily for imaging the sun across a range of extreme ultraviolet wavelengths. While it cannot pass as close to the sun as the PSP, the Solar Orbiter still needs heavy-duty thermal protection. Thin sheets of titanium foil pinned to an aluminium honeycomb make up a heat shield with 5 peepholes for instruments. Its solar panels rotate to prevent overheating. Like the PSP, the Solar Orbiter used the gravitation of Venus to augment its orbit. During its initial cruise phase, it also swung back past Earth for added gravitational assistance. It's in a resonant orbit with Venus, and soon it will use that planet's gravitation to bend it out of the ecliptic. This tilted orbit will, for the first time, allow pictures of the solar poles. In September 2023, the Solar Orbiter returned this view at the 171 angstrom wavelength. It reveals the transition from the sun's lower atmosphere to the corona. The waving, slender threads are plasma from the interior, following the changing magnetic field lines.
So it's very fascinating to see for the first time the high resolution of images of the solar corona. The images we are getting down now with perihelion are perhaps the best ever recorded. And so we are seeing stuff there that has not been recorded before.
At the same time these images were captured, the Parker Solar Probe was passing the Sun at just 7.26 million kilometers. By matching the data from both craft, solar physicists could use the solar orbiter to see the origins of the solar wind that was being recorded by the PSP. The solar orbiter also carries a coronagraph. It's a useful instrument for observing the corona, which is usually not visible because of its proximity to the brilliant sun. The best coronagraph we have occurs when the moon blocks the sun during an eclipse. By sheer coincidence, the relative distances and the relative diameters of the sun and the moon allow the moon to occlude just the sun, providing a clear view of the parts of the corona close to the solar surface. But the observation time is limited to just a few minutes. Soon, a new pair of European satellites called Proba 3 will test a new technique for observing the corona. The occluding spacecraft will use lasers to accurately position itself 144 meters from the observing spacecraft. They will fly in precise formation with the occluder casting a tiny shadow upon the observer's instrument, accurately blocking the sun's disk. This will deliver images of the corona closer to the edge of the sun than have so far been available. It is this area of transition that solar scientists want to understand. Regular contact between the science teams of the Parker Probe and the Solar Orbiter are maintained to plan future joint investigations, especially when their craft will be in complementary positions. Solar researchers are hoping to understand any interconnection of solar phenomena so that they can build computer models that could be helpful in predicting the sun's behavior. This is how weather surfaces on Earth work. Powerful computers combined with extensive high-resolution data sets have seen great improvements in the accuracy of weather prediction. In the pre-technology world, solar weather resulted in beautiful auroras. Today, if a major coronal mass ejection unexpectedly collided with Earth, a variety of events could unfold. The International Space Station orbits at around 400 kilometers, yet there is drag from the very thin air that still persists at this height. To reduce friction, its solar panels are swiveled edge-on when the Earth blocks the sun. Even so, the space station loses around 75 meters in altitude every day, and regular boosts from visiting spacecraft or firings of its own propulsion system are required. Solar storms heat the upper atmosphere, causing it to swell. During heavy solar activity, the ISS has lost as much as 1,500 meters in one day, and waves of charged particles can disrupt sensitive electronics. Low Earth orbiting satellites are affected in a similar way, and without adequate warning, spacecraft have been lost. SpaceX's fraternal company Starlink owns 60% of operational satellites and continues to add more. The internet provider launches up to 60 Starlink satellites at a time to low Earth orbit. Each is equipped with an ion thruster, and they spread out, gaining height after deployment. Early in 2022, a moderate coronal mass ejection was detected from the northeast quadrant of the Sun. Several days later, Starlink launched 49 satellites. The timing couldn't have been worse. The satellites did not have the power to break free from the thicker atmosphere, and 38 of the spacecraft fell back to Earth. A study following another geomagnetic storm in May 2024 revealed that 2,000 satellites had to maneuver after being pushed out of position. In these crowded orbits, this type of event significantly raises the chance of collisions. In March 1989, after 2 coronal mass ejections, Quebec was blacked out as circuit breakers protecting the electricity grid were tripped. Long power lines and a unique geological substrate inhibiting excess voltage running to ground made the province vulnerable. There have been advances in power grid design and in shielding the delicate electronics necessary for communication with and control of spacecraft. Techniques for monitoring the sun's behavior have improved, but the experts know that a major plasma wave that directly hits the Earth could still overwhelm these precautions. And soon, for the first time since 1972, space flights will take humans beyond the protection of the Earth's magnetic field. The Artemis program aims to return astronauts to the Moon and establish a lunar orbiting outpost. Humanity's understanding of the Sun is basic. Close monitoring of its behavior and the accumulation of long-term data sets will give our technological world deeper knowledge of the star upon which we depend.